Hey everyone, today we're going to be starting a new unit on energy. Specifically, our lesson today is going to be on work and energy, and more specifically how work, energy, and power are related. And we've all heard of energy before, but as far as a concrete definition, not sure that we're all on the same page with that, but this one is relatively simple. And energy, in its simplest form, no pun intended, is the ability to do work. Change that to the right pen here. The ability to do work. In a way, you can kind of think, well, I have to have energy in order to get to my job down at the grocery store or wherever it may be. If you don't have energy, it's going to be more difficult for you to do work. You might think of it as doing your physics homework at night. I need to have energy in order to do this work. But depending how you look at it, even doing your physics homework might not actually be doing work, even if you are expending energy in some way. It's going to ultimately come down to how we are applying that energy. So energy is a scalar quantity, which means it is not described by its direction. And when work is done either by a system or on a system, the total energy of that system is changed. We're going to alter it in some way. So on to our definition here of work. Now work, we'll see how this applies to your current view of work. So work is the transfer of energy to an object when the object moves due to the application of a force. So if we apply a force and put some energy into something, and we cause that object to move, then we are doing work. There's a couple keys here that I'm going to highlight in a second. First, work we know is a scalar quantity. You don't have to describe the direction of your work, just that you're doing work. Now, if you think of a person kind of standing here and lifting a box off the ground and to try and move it up above their head. This guy's going to have to hold the box, so I'm going to have to take his arms back there for a second. So this guy's going to hold the box above his head. Now to move the box from the ground up to above this guy's head, let's say it is 2 meters, work is done. Work is done to move the box above your head. You're applying a force to raise the box against gravity, to hold it above your head. You're moving it 2 meters from the floor to above your head. So we're doing work. We're transferring energy from our body to the box to raise it, to move it above our head. Holding the box is a different story. If we hold the box above our head, are we doing any work? No. And the key here is that when we're holding it, there is no movement. And this is going to be key to determining when work is done. The object has to actually move. So if you're standing there holding something, even if you're sweating and blue in the face trying to hold that box above your head and arms are quivering, you're not doing any work. Because that object has to move. It has to move some kind of distance. Now we can determine the amount of work that's done, represented by W. And that is equal to the product of the force along the direction of displacement. And we're going to multiply that force times the displacement, represented with a lowercase d, of the object. So we know displacement is a vector quantity. It is described by direction. So the work that we do is going to be in the direction of the displacement of the object that we are moving. Now the work done on the object produces a change in the object's total energy, which we represent as delta E sub t, or total change in total energy. So the work is due to applying a force to move an object some kind of distance, so it's the product of those two quantities, or it's also equal to the change in total energy. So those are some ways that we can figure out how much work is being done. Now in this equation, the force, we know we measure force in newtons. Displacement is measured in meters, their standard unit. Work is change in total energy. We can express that as what we call a Newton meter, or in Newton times a meter, force times a distance. So let's break this down a little bit. Two ways that we'll represent this. 1 Newton meter is equal to, if we break down a Newton, 1 kilogram times a meter per second squared. Times another meter. So to kind of combine that, we say that 1 kilogram, I don't like that K there. So 1 kilogram times, if we move that meter around, it becomes a meter squared per second squared. This is going to be a new derived unit, which we call a joule. Now the joule, as I said, is a derived unit that's equal to the work done on an object when a force of 1 Newton produces a displacement of 1 meter. So it's going to give us a way to quantify how much work is being done, how much energy is being expended while doing work. So the amount of work that is done is independent of the time that the force acts on the object. So it doesn't matter how long it takes you to pick up the box and put it above your head. The work's going to be done over the distance to get it above your head. Assuming we're not changing the force. So time's not going to matter. You can take all the time in the world, you're going to keep doing work, you're going to keep doing the same amount of work as long as the force and the distance don't change. But the time it takes to complete that task doesn't matter. So when we apply a force to a mass, but the mass doesn't move, as I said, no work is done. The object itself has to actually move. So if a student was to hold an object or a box at a constant height above the ground or above their head, no work's going to be done, no matter how heavy the object or how much effort, how long that student is going to expend the energy to hold the box off the ground or hold it above their head. So the key here for work is that we apply a force to an object to move it a certain distance, and the object has to move a certain distance. Now power is the rate at which work is done, and you might have some experience with this depending on how familiar you are with your energy consumption in your home. I'll get to that in a second. But power, like work, is a scalar quantity, so it's not described using its direction, only its magnitude. And we use the equation of work over time to determine how much power is expended. Now to kind of break this down a little bit, we know that work is equal to force times distance. We had just talked about that. We know from earlier that our average velocity is equal to our displacement over time. So to kind of combine these here, we can say that, well, power is equal to work over time. If we substitute our units for work, we can say that that's equal to our force times distance over time, or equal to our force times our average velocity, which is distance over time. We will be using various forms of this equation. So F is the force applied to the object that's going to cause it to move with some type of average speed. Remember to find average speed. Take our initial plus our final and divide it by 2. We can also take the displacement over time. Depends what we are given in the problem. So the units for power are joules per second. That's an S there, joules per second. Or another term that we can use for a joule per second or for power is something that we call watts, where 1 watt is equal to 1 joule per second. So it's the rate at which work is being done. Power is inversely proportional to time, which means that if we complete a task in less time, the more power we are going to need to expend in order to complete the work. If we increase the amount of time to do our work, we're going to decrease the power required to do that. Now, if you go outside and take a look at your electric meter, you're going to see this little dial inside the meter that's going to be turning, and that is measuring how much electricity you use in the home based on what we call a kilowatt hour. How many kilowatts of power are being used every hour? To kind of break this down a little bit, 1 kilowatt hour is equal to 1 100 watt bulb burned for 10 hours. So that'll be 100 watts burned for 10 hours. That would be equal to 1,000 watts or 1 kilowatt hour. And this is how electricity is, or electrical power is measured in your home, and ultimately how you would be billed for the usage of that electrical power. I'll show you guys some examples here in my next video. For now, I'm going to leave you with a joke. I was reading a book earlier, last night actually, on helium, and I'll bring it in so you guys can read it. And I promise you, just like I couldn't, I promise you that you will not be able to put it down. Have a great day.